I hope you're doing good. Let's dive right into chapter 3. Get the PowerPoint up and going. Here we go. Okay. So chapter 3 is the first chapter that we are actively talking only about organic chemistry. So chapter 1 and chapter 2 also had a lot of general chemistry in it. So it was a lot of review from general chemistry, a lot of foundational skills. In chapter 3, we're going to start going functional group by functional group and talking about those classes of substances and their properties, how we name them, how we make them, things that you need to know about them, and also reactions of that. So we're going to start with alkanes. Alkanes are our simplest group of organic compounds. And let's look at the learning objectives. Okay, so we want to be able to identify alkanes, alkenes, and aromatic hydrocarbons and draw their structural formulas for examples. So chapter 3, we're going to start out with just talking about hydrocarbons in general. And so you'll be able to identify alkanes, alkenes, and aromatic hydrocarbons. For alkanes, if I give you the IUPAC name or the common name, you need to be able to draw the structure and give the molecular formula. And you also need to be able to draw isomers of alkanes and cycloalkanes and use IUPAC rules to name alkanes, cycloalkanes, and bicyclic alkanes. You need to explain and predict trends in the physical properties of alkanes. So boiling point is really a big deal with alkanes, and then melting point, that kind of thing, because we can use those properties to identify alkanes, unknowns. Then we're going to use Newman projections to compare conformational energies and predict the most stable conformations of alkanes, and show how torsional energy varies as the dihedral angle changes. We're going to talk more about this as we get there. Compare the energy of cycloalkanes and explain how their angle strain and torsional strain combine to give the total ring strain. Draw accurate cyclohexane chair conformations and then place axial and equatorial groups in their proper positions with correct bond angles, and then predict the most stable conformations of mono and disubstituted cyclohexanes by placing larger groups in the equatorial rather than the axial position. Okay, so keep these learning objectives in mind as you're going through your practice problems and things. They're informative as they are, and we're going to talk more about them. Okay, so let's talk about hydrocarbons. So hydrocarbons are a class of compounds that are made only of carbon and hydrogen. So we only have carbons and hydrogens in hydrocarbons. So alkanes are our simplest hydrocarbons. We don't have any double or triple bonds, and a lot of times we will say that they are saturated or aliphatic. We say that they're saturated because it holds the maximum number of carbons that they can hold. Alkenes have at least one double bond within them that makes them an alkene, okay? And then alkynes have a triple bond somewhere within them as well. Alkanes end in ANE, the nomenclature does, okay? Nomenclature is how we name these compounds. Alkenes end in ENE, alkynes end in YNE. And then we have aromatics. In aromatics, we have this benzene ring. Benzene ring is a resonance stabilized 6-membered ring, and we draw its Lewis structure as double bond, single bond, double bond, single bond, double bond, single bond. You get it. And so we're going to have this ring here in all of our aromatic compounds. This example is ethylbenzene. A lot of times they'll end in benzene, but there's some exceptions there. We'll talk more about those at the beginning of organic too. So what are alkanes? So the general formula for alkanes is CnH2n plus 2. Now let's talk about what this means. That means that N is however many carbons we have. So if we have an alkane, a regular alkane, not a cycloalkane, but a regular alkane, then we're going to have, if we have one that has one carbon, okay, then the number of hydrogens that we're going to have is 2n plus 2, okay? So 2 times 1 is 2 plus 2 is 4. So if we have a compound that only has one carbon, we should have 4 hydrogens with it if it's a straight, just regular alkane. So we find these alkanes in a lot of fossil fuels, okay? So everything from natural gas, petroleum, those kind of things. The smaller alkanes have very low boiling points and are gases. So up until we get to butane, butane is our first liquid, first alkane that is a liquid at room temperature. Propane, ethane, and methane are all gases at room temperature. We're going to talk about why that is when we get there. Okay, so here is methane, ethane. This is also called ethylene, but its systematic name is ethane, and then propane. And these are all gases. Their boiling points are in the minus even. They're not even above 0 Celsius. Okay, the CH2 group is called a methylene group. So the way that alkanes vary, especially when we're not talking about cycloalkanes, we're just talking about regular alkanes, is how many different CH2 groups they have. So a series of compounds that only differ in the number of methylene groups or the number of CH2 groups are known as a homologous series. Okay, so here we have methane, here we have ethane, okay, and then we add in a CH2 group from there right in the center. We have propane. If we add in 2 CH2 groups, we have butane. So the chains just get longer and longer and longer. And sometimes it's actually written this way, where we have an H on one end and an H on the other end, and then we write our CH2s and however many CH2s we have. Okay, so if we have 5 CH2s, 1, 2, 3, 4, pentane would have 5 CH2s and then H's on the end. Sometimes, not very often do we write that way, but if you see it that way, don't get confused. So here's some small alkanes: methane, ethane, propane, butane. Butane's a liquid at room temperature. It's known as lighter fluid. It's in like cigarette lighters and things like that. It's a liquid at room temperature. So those are some small alkanes. So if we add up, look here. 1, 2, 3, 4 carbons, okay? Based on our CnH2n plus 2, if we have 4 carbons, okay, then this would be 8 plus 2 would be 10. So we should have 10 hydrogens, okay? So 2, 4 plus 3 is 7 plus 3 is 10. And we do with butane. It's C4H10. So this is a huge table, and you don't have to memorize this, okay? This is just showing you how the physical properties change when we have unbranched alkanes. And sometimes they're called N-alkanes or normal alkanes. In other words, they're just big, long chains of carbon and hydrogen. So we're not talking about branched alkanes, we're talking about N-alkanes. Okay. So if we look, we're moving from methane, there's octane, that's the active ingredient in our gas, butane's lighter fluid, propane you use to cook with, okay? My parents have a house out in the country and they use propane in a big tank. And then these just get bigger and bigger and bigger. So here are the number of carbons in it, okay? So all the way to tricontane, which has 30 carbons in it, okay? So here's our structure. Oh, sorry, I'm yawning. Here is our structure here, okay? And you can see, look, watch. As we move through here, here's our boiling point, okay? See, notice that our boiling point goes from very low to actually really, 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 really big. Okay, so as our chain length increases, our boiling point increases. Now, our melting point is a little bit more complicated than that, but you can see it does follow that same pattern. But there are other factors here with melting point that we're going to talk about. As far as density goes, density does increase slightly as chain length increases. So everything goes up as chain length goes up. Boiling point goes up, melting point goes up, density goes up as our chain length increases. So that's pretty easy to remember. These on the whole are very not very dense substances, even less dense than water. Okay, so water is about 1 gram per milliliter. So these are all less dense than water, which means that they would float on top of water. These are also non-polar molecules, okay, and so they would not dissolve in water. Okay, so let's look at butane. We're going to talk about constitutional isomers. So constitutional isomers, we've talked about them before when we talked about isomers. Constitutional isomers are compounds that have the same molecular formula, but their carbons are connected differently, okay? So one carbon is connected differently to the other, okay? Or connected to a different carbon even is what we need to think about. Whereas structural isomers, constitutional isomers, they have the same molecular formula, but the carbons are connected differently. So here, let's look at this. This is N-butane. It's one big long chain. That's the N, the normal. Okay. And then isobutane is where we have 3 carbons, but we have a carbon connected to the center carbon. So we still have 4 carbons. We would call this an isobutyl group. But one carbon, instead of being connected to the end, I gotta stop yawning, y'all. It's connected to the second carbon. So here's some other examples: N-pentane, isopentane, and neopentane. So how do we name alkanes? So this is our first kind of big dive into nomenclature. So let's get started. When we're talking about nomenclature, we need to talk about IUPAC. IUPAC is the International Union of Pure and Applied Chemistry, and they're the governing body that determines what names are acceptable and what names are not acceptable. For the most part, we use systematic names to name all of our organic compounds. We'll have systematic names and we'll have common names, and common names are generally not accepted. But every now and then, if a common name has been around long enough, then it will be accepted as an IUPAC accepted common name, okay? But for the most part, we're just going to stick to the systematic names of everything, unless I tell you differently. So IUPAC and systematic names, the IUPAC name, okay, is the standard method that's used internationally to name compounds. It uses the longest chains of carbon as the main chain, and then a couple of common names are kept, like methane, ethane, propane, and butane. So here are IUPAC rules, and this is something kind of like unit conversion factors were in general chemistry, where we're going to start simple and go through the process, and you'll learn the process, and then throughout this semester and next semester, we will build onto this process with our different functional groups and different things, okay? So let's talk about these rules. The very first thing that you need to do is find the longest continuous chain of carbon atoms and use this chain as the base name of the compound. Sometimes this is called the base chain or the parent chain. You'll hear me call it the parent chain, because that's one way that I usually call it. We number the longest chain beginning with the end of the chain that is nearest a substituent. Okay, and you'll get the hang of this when we apply these rules, okay? And then we name each group attached to the longest chain as alkyl groups. We give the location of each alkyl group by the number of the main chain carbon atom to which it is attached. This will make more sense when we do it as well. And then we write the alkyl groups in alphabetical order regardless of their position on the chain. So we always put our substituents in alphabetical order. These are not always alkyl groups. It says alkyl groups, but these could be halogens like bromo, chloro, fluoro, okay? We still will put them in alphabetical order. So let's look at this. Let's talk about the main chain. Sometimes I call it the parent chain. So we're going to find the longest chain of consecutive carbons. And it doesn't matter if they're written from left to right. These may be drawn kind of all over the place. So you're really going to have to kind of try over and over again to make sure that you can find the longest chain of consecutive carbons. So let's look at this example. If we just started here and counted 1, 2, 3, 4, 5, that would only be a 5-carbon chain with an ethyl group. We've got to think harder about this, okay? So let's start here. 1, 2, 3, 4, 5, 6. We can actually find 6 carbons in a row if we kind of turn the corner on this. And then we have a methyl group attached. Now, when we're numbering these, we don't want to start at this end and number around because we want to start at the end where we come to our first substituent first. So we would actually number these carbons 1, 2, 3, 4, 5, 6 in that order because we want to start numbering where we come to our first substituent first. In other words, whatever numbers are included in our nomenclature, these are called locants. The numbers are called locants. We want our locants to be as small as possible, okay? So ultimately, no matter what, and no matter how many locants you have, you always want those numbers to be as small as possible. So if we started numbering here, 1, 2, 3, 4, okay, our methyl group would be attached to our 4th carbon. Whereas, so this would be 4-methylhexane. Whereas if we start numbering here, 1, 2, 3, 4, 5, 6, the methyl group is attached to our 3rd carbon, making it 3-methylhexane. 3 is smaller than 4, so we need to start numbering at this end of the molecule. So here are some other examples. So this is a big, crazy molecule, not as big and crazy as it gets, okay, but pretty big and crazy, and we need to find the longest chain. Ooh, it's been a long day. I'm sorry, I can't stop yawning. So if we start here, 1, 2, 3, 4, 5, 6, okay, we would only have 1, 2, 3, 4, 5, 6, 7. We have a 7-carbon chain, but only 3 substituents, okay? If we start numbering here, 1, 2, 3, 4, 5, 6, 7, we have a 7-carbon chain with 4 substituents. And when we have 2 chains of equal length, we want to use the chain with the greatest number of substituents. So this one is the one, this is how we would want to do that. So number the longest chain beginning at the end of the chain that is nearest of substituent. Okay, so we have 2 options here. We can start numbering at the top, or we can start numbering at the bottom. If we start numbering at the top, 1, 2, 3, we come to our first substituent at carbon number 3. If we start numbering at the bottom, 1, 2, we bump into a substituent on the 2nd carbon. So we definitely want to start at the bottom. 1, 2, there's a substituent. That's a methyl group because it only has 1 carbon. On the 3rd carbon, we have an ethyl group. On the 4th carbon, we have a methyl group. On the 5th carbon, we have a methyl group, okay? So this would be, so our methyl groups are on 2, 4, and 5, and then we have an ethyl group on 3. So we can use our prefix tri for our 3 methyl groups. And then we just need to put the locant for our ethyl group, okay? So and then we also, E comes before M. Now, when we use a prefix like tri, di, tetra for however many groups we have, we don't include that in the alphabetical order, as if things couldn't get any more complicated, okay? So ethyl comes before methyl, so we have 3-ethyl, 2,4,5 trimethylheptane. Now, sometimes you will have methyl groups that are on the same carbon. So let's say that this methyl group was attached to this carbon here, this second carbon, and there wasn't a hydrogen, okay? We would still write trimethylheptane, but we would actually list the number 2 times. So it would be 2,2,5 trimethylheptane. So if you have a tri prefix, you have to have 3 locants, okay? You have to specify, even if 2 of them are on the same carbon. So here are alkyl groups, okay? This is how they're named as an alkane. So we have methane, ethane, propane, butane, pentane. So when they lose a hydrogen and are attached to a longer chain, we call this a methyl group, this an ethyl group, this a propyl group, and then here we have a 4-carbon chain is a butyl group, a 5-carbon chain is a pentyl group. Okay, so we take off the ane and add YL. So you need to memorize these. These are some common alkyl groups that we see. Okay, so a methyl group for sure. We see those everywhere. It's really important that you know what this is. A 2-carbon group is an ethyl group. And then we have a propyl group, which is a 3-carbon chain. But sometimes we have 3 carbons that are attached to our parent chain, but they're attached to the central carbon to the parent chain. When this happens, we call it an isopropyl group. Here's our regular butyl group. Sometimes these are known as N-butyl for normal, okay, which just means that they're all one long chain. Okay, and then we have an isobutyl group where we have this kind of branching situation where we have a carbon, the 4th carbon is actually attached to the central carbon in the butyl group. And then we can have what's called a sec butyl, where it's attached to the adjacent carbon that's attached to the parent chain. And then what's called a tertiary butyl, where we form this T shape, okay? So we have a carbon with 3 methyl groups attached to it. And that's actually called a tertiary butyl or a T-butyl or a tert butyl group. Okay, so let's talk about applying the naming rules. Nomenclature 101 is the website that is super helpful for you. You go on there and do as many practice problems. They'll give you as many practice problems as you need to tease out nomenclature. And they can give you the English name and you draw the organic molecule, or they'll give you the organic molecule and you give the English name. You need to be able to do both of those, just like when we were doing chemical nomenclature in general chemistry, where I give you the English name and you give the molecular formula, that kind of thing. Okay, so we need to name groups that are attached to the longest chain as alkyl groups. Oh my gosh, I can't stop yawning, y'all. Okay, so here we have 1, 2, 3, 4, 5. We have a 6-carbon chain. We're going to start numbering at this end because we come into contact with our first substituent on carbon 2. If we were to start at this end, 1, 2, 3, we would run into our first substituent not until the 3rd carbon. So this end is our end to name. Okay, so then we find what substituents we have. Here is a methyl group. Here is an ethyl group. Okay, so this is going to be 2-methyl, 4-ethyl, but we have to put it in alphabetical order. And ethyl comes before methyl in alphabetical order. So this would be 4-ethyl, 2-methyl hexane. Okay. When 2 or more of the same substituents are present, we use the prefixes di, tri, tetra, to indicate how many different groups there are. So in this example, we have decane. So we have a 10 carbon chain. 1, 2, 3, 4. Okay, if we started numbering at this end, we wouldn't run into a substituent until carbon number 4. So we're going to start naming at the right end and move to the left because our substituent is closer to that end. Okay, so we'll number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from the right to the left. This gives us a methyl group on carbon 2, carbon 5, and carbon 7. Okay, so that's exactly what we write. 2,5,7 trimethyl decane. Oops. Okay. These are iso groups, and you do need to memorize these because these will come up, and the earlier you memorize them, the better you'll end up being. Okay, so here's an isopropyl group where we have 3 carbons and they're attached at the center carbon to the parent chain. So a parent chain would be here. Here's the isobutyl group where we have 4 carbons, but we have a little bit of lengthening chain. Remember, if there's a methyl group attached here, that's actually a secondary butyl group or a sec butyl group. But this is an isobutyl group. This is isobutane, okay? It's not attached to anything. It's not a group. It actually is its own molecule. And then an isopentyl group where we have 5 carbons and we have this CH3, CH, CH3. Okay, so give the structures of 4 isopropyl octane and 5 T-butyl decane. So if you want to pause it and see if you can work this out, go for it. I'm going to write it down on a piece of paper and then hold it up to the camera. Okay. So the first thing that I do is I need to look at, let me actually use my drawing. Let me see if I can get there. Nope. Here we go. Okay. So I'm going to draw. Okay, perfect. I'm going to look at the parent chain first. Okay. That's the first thing I want to look at. And that tells me how many carbons I have. Okay. And so then I'm going to draw that many carbons. So octane, we should have 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Of course, my pen's going to run out. Should be more prepared. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I like to draw a skeletal structure because it's quicker than drawing a whole bunch of other things. So I'm going to draw an 8 carbon parent chain. Then I'm going to look and see what's connected to that 8 carbon parent chain and also where it's connected, the most important thing. Okay, so I'm going to count 4 carbons from either side because we can choose the way that this molecule is drawn. Okay, so I'm going to draw an isopropyl group on carbon 4. An isopropyl group is Y-shaped. So I have an isopropyl group on carbon 4. Let me draw my numbers. See if you can see that. And the Y-shaped is our isopropyl group. So we have carbon, 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 and it's attached to the parent chain at the center carbon. Okay, so that is 4 isopropyl octane. So then let's talk about 5 tertiary butyl decane. Okay, so the first thing I'm going to look at again is the parent chain and how many carbons are in it. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? Because decane means that we have 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Always check your work. I'm super scatterbrained, and you guys know that. And because of this, I have to just kind of check my work over and over and over again. It's something that I've learned how to do. Okay, so a T-butyl, okay, is a tertiary butyl group, which means that it's going to be shaped like a cross. Okay, so I'm actually going to have a central carbon and then kind of 3 methyl groups around it. And I know that my tertiary butyl group is going to be on carbon number 5. Okay, so I'm going to number my carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me show you. This is my parent chain. This isn't my full molecule. This is just my parent chain. Okay, so I have 10 carbons there and all the hydrogens that go with them, but I don't have to write those because this is a skeletal structure, and that's the beauty of a skeletal structure. Okay, and then I'm going to draw, I'm going to have to draw right through my 5 for my tertiary butyl group. Okay, and my tertiary butyl group is going to come down because it's on carbon number 5. We draw it down. And so I have 1, 2, 3, 4 carbons in my tertiary butyl group. Okay, so that is 5-T-butyl decane. Let's see how your book draws it. Let me clear all my drawing. So 4-isopropyl octane has a chain of 8 carbons with an isopropyl group on the 4th carbon. Good, we got that part right. And then a 5-T-butyl decane has a chain of 10 carbons with a T-butyl group on the 5th. So you can draw it in its condensed structure if you would like, and this is what it would look like. So this is good because it's a little bit different than I drew it. Both are acceptable, okay? Skeletal or condensed, either one. I guess this wouldn't be condensed, this would be Lewis structures. Okay, organizing multiple groups. So when 2 or more substituents are present, we're going to list them in alphabetical order. When 2 or more of the same alkyl substituents are present, we're going to use our prefixes, di, tri, tetra, etc. In order to avoid having to name the alkyl group twice, okay? And we're going to include a position number for each substituent, even if it means repeating a number more than once, okay? These are called locants, L-O-C-A-N-T-S, locants, okay? It's like your house number in your address. It just tells us where what is going on, okay? So here are all of the prefixes that go along with that. And this final rule deals with naming compounds that have more than one of the same substituent. Okay, so we looked at this example before. We have 3 methyl groups, okay, and an ethyl group. Ethyl comes before methyl, so our ethyl is on carbon 3, so we write 3-ethyl, and then 2, 4, 5, trimethyl heptane. But remember, our prefix doesn't count toward our alphabetical order, okay? So sometimes you'll see dimethyl after ethyl, and that's because our prefix, we don't look at our prefix to determine our alphabetical order, only our actual substituent. Except in the case of isobutyl groups, okay? That's actually the name of the group. So that isobutyl group, we'd go by I, not B. Okay. So here's complex substituents. So complex alkyl groups are named by using the longest carbon chain. Carbon number 1 of the alkyl group is the carbon that is attached to the main chain. I'm really trying not to yawn, and I'm so sorry. Okay, so this group here has a 3-carbon chain with an ethyl group on the beginning and a a methyl group here. So this would be a 1-ethyl 2-methylpropyl group. We always start with carbon number 1 as the one that's attached to the main chain. You could start numbering, let's see, 1, 2, 3. That'd be more complicated. So you still want the one that has the most numbers of carbons. 1, 2, 3, 4. So this would be a trimethyl-butyl group. 1, 1, 3, because both of these methyls are attached to the same carbon number 1. Okay, so give the systematic name for the following compound. I am actually going to draw on this where you can see, okay, because we have a lot of options here as far as naming our parent chain. Okay, so let's start and see if we can figure out, oh, I lost my mouse. There it is. There's a glitch in Zoom where when you go to draw, you can lose your mouse. Okay, so let's just start naming at a bunch of different places and see, numbering at a bunch of different places, see how we can find our longest chain through all of this. So I am going to draw here. Okay. I'll use different colors. So, yeah, there we go. Okay. So if we start here, 1, 2, 3, 4, 5, 6, 7. Okay, so there's a 7 carbon chain. If we start here, and then we can go 1, 2, 3, 4, 5, 6, 7, 8. So that's an 8 carbon chain. That's good. That's better than 7. Let's see. We can start here and go 1, 2, 3, 4, 5, 6, 7. That doesn't help us get it any longer. I'm trying to think if there's any other options that could be. I think our red is still good. It's going to be the longest no matter what we do. We could draw 1, 2, 3, 4, 5, 6. That's only 6. That's not the longest. 1, 2, 3, 4, 5, 6, 7. I don't think I can get anything longer than 8. I think 8 is going to be our longest. Okay. So 8 is the red. So I'm going to clear this and go back. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. If we start numbering here, 1, 2, 3, 4, 5, 6, 7. That's not right. I missed one. 6, 7, 8. Okay. If we start numbering down here, then we're going to run into 2 methyl groups on our second carbon. If we start numbering here, so on our second carbon, if we go the other way, I'm going to draw this in purple. 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 options. We can number from the bottom to the top, kind of the top right, or we can number from the top right down to the bottom. If we use the red, like I said, we're going to run into 2 methyl groups on carbon 2. But if we use the purple, we actually won't run into a substituent until we get to carbon 3. Okay, so that's no good. We don't want to do that. we don't want to use, we always want our numbers to be the lowest that they can. Okay, so I'm going to erase the purple and we're going to use the red numbering. And let's talk about our different substituents. So I'm going to circle methyl groups in blue. Okay, so we have a methyl, oh, if I can. Okay, so here's a methyl group, here's a methyl group, here's a methyl group, and here's a methyl group. Okay, and then this guy here is an isopropyl group. Okay, so now that we've organized all of our substituents, we've named our parent chain, it's going to be octane. Okay, let me actually type that. I think I can do this. Okay, so it's going to be an octane. We know that. And we have 1, 2, 3, 4 methyl groups. So, and then an isopropyl group. So I comes before M in alphabetical order. So it's going to be 4 isopropyl and then we're going to, it's going to be 2, 2, 3, 6 because we have 4 methyl groups. 2, 2, 3, 6 tetra, no space, because that's our prefix for 4, tetramethyl octane. We put, there we go. Oh, and that's all one word. We're going to write that as all one word. Ooh, if I can get back to it. I made a mistake and I can't get back to it. Okay, so you're going to leave out, don't put a space right there between the tetramethyl octane. Okay, so do you see? So these 2 methyl groups are on the same carbon, so that's 2, 2. And then this methyl group is on the 3rd carbon. So that's our 3. And then this methyl group's on carbon 6. And then our isopropyl group is on carbon 4. So let me clear everything. Oh my goodness. Okay, we got it exactly right. Very, very good. Yay. Now, notice they went from here, okay, through carbon 8, but that doesn't make a difference because it's still a methyl group on carbon 2, okay? Still a methyl group, 2 methyl groups on carbon 2. We couldn't have gotten our chain any longer. Great job, guys. Okay. So our degree of alkyl substitution, so we can have very complex side chains. That's all this is saying is here is a very complex side chain. It's a 1 ethyl 2 methyl propyl group. Okay, it has a complex side chain. So this is how we would write complex side chains. We would actually put them in parentheses and put the locant of where they're found there. Okay, let's talk about boiling points of alkanes. So I showed you on that chart that as the number of carbons in an alkane increases, the boiling point also increases. But I didn't tell you why. And the reason is that we have larger surface area, okay? So when we have this larger surface area, now remember that van der Waals attractions, London dispersion forces, or London forces, are a type of van der Waals attraction. These attractions, they're intermolecular forces, okay? So these are types of intermolecular forces. None of these compounds have oxygens, nitrogens, so we're not talking about hydrogen bonding or anything like that. These are all non-polar, so the only type of intermolecular force that applies to them are London forces or van der Waals attractions. These are kind of, we can use these words interchangeably for this level, of course. The longer the chain is, the more that these guys kind of stick together side to side, okay? And when they're held together, that prevents them from escaping into the gas phase. It's like somebody holding their ankle, kind of keeping them down into the liquid phase. Okay, now melting points also increase as the carbon chain increases, but what's interesting is that alkanes that have an even number of carbons have higher melting points than those with an odd number of carbons. They still increase as the chain length increases, but each time we bump to an even number of carbons, it increases more than what we would expect it to increase. So how do we make alkanes? Well, for the most part, we can just extract them from the earth, okay? Because most of them are obtained from petroleum and petroleum byproducts. If you have ever seen a refinery, such as it used to be called the Williams Refinery, now it's Valero in downtown Memphis. These are everywhere. My parents live in South Louisiana, and they're ubiquitous there. They have these large towers, and these large towers are giant fractional distillation columns. You'll be learning more about fractional distillation in lab, hopefully. But fractional distillation is where we're boiling something at the bottom, and we have a giant column that cools off as it gets taller. Okay, and as it gets taller, the things that condense, okay, at certain points away from the heat will come off. So we can separate things by their boiling points. So with a lot of these petroleum products, we'll start with crude oil and purify them or refine them at the refinery based on their boiling points. Okay. We can also use something called catalytic hydrocracking, okay? And this is where we use, or sometimes it's called steam cracking, where we take a long chain alkane, or even things that have double bonds and things like that, and we use hydrogen gas and heat and a catalyst, and we can break it down into shorter chain alkanes. Catalytic cracking, we can actually take heat and a catalyst and create shorter chain alkanes and alkenes. The difference is the absence of hydrogen gas. Okay, so major fractions that are obtained from distillation of crude petroleum. So crude petroleum is oil that comes straight from the ground. It's just the raw materials, the raw oil that comes straight from the ground. Here in our fractional column of our refinery, okay, there's another name for these tall buildings. It'll come to me, I can't remember. So under 30 degrees, we're looking at very short chain alkanes. Okay, so we're talking about ethane to butane. And this is from petroleum. The fraction is called the petroleum gas fraction. And this is used liquid propane gas for heating. Okay, 30 to 180, we're looking at carbons, a number of carbons from butane all the way to nonane, and this is gasoline, okay? This is our fraction of gasoline. Remember, gasoline, the main component of gasoline, or the one that your car really craves, is the octane. But all of these carbons contribute to the combustion power within your engine. But an octane rating tells us exactly how enriched the gas is. Okay, so you guys can read through this. We go all the way from gasoline to paraffins. Okay, so paraffins are very long-chained carbons. Waxy, we end up with waxy things, and we'll talk more about this when we get to biomolecules, because we're actually headed toward, there's a lot of paraffins and waxes that are made naturally, like from bees. Okay, so let's talk more about information about alkanes and the ways we can represent them. So methane, I've got my modeling set here. Let's see. So methane, we can represent it in the ball and stick model, okay, which is the very central model that you see. And then there is the line bond angle, which we're working on drawing. Now, when we have a line bond angle, so let me actually get my model of methane. So here is my methane here. It's sp3 hybridized. It has all single bonds, which means that it's tetrahedral, okay? So tetrahedral means that if we were to connect all the lines, okay, we would have a triangular sided pyramid, which is called a tetrahedron. Okay, so the bond angle from here to here is approximately 109.5 degrees. Okay, tetrahedral. Now, this other guy over here, this is a space filling model, and space filling models can be exceptionally helpful when it comes to showing us things with space, like how much space a nucleophile needs to get in for an SN2 reaction, which we're going to talk about when we get to alkyl halides. Okay, so ethane. Ethane, I have purple things here, but these are actually hydrogens if we're talking about ethane. So ethane has 2 carbons. Now remember, what's really important about our alkanes is because they don't have any double bonds, we have free rotation around that sigma bond. So this is a sigma bond here because it's a single bond. And remember, a sigma bond is the first bond in any multiple bond as well. And so because of that, sigma bonds are directly within the internuclear axis, which means it's it's in between these 2 atoms right here. A sigma bond occurs right in between, whereas a double bond kind of does like this, okay? And it occurs above and below the internuclear axis. But because this is a single bond, it allows free rotation around that central bond. We're going to talk more about that in just a second. Now, conformations are different. Conformations are different arrangements of atoms caused by this rotation, okay? So if we look at it on the end, let me see if I can get this where you can see it, okay? We can actually make this molecule, so you can look here, where the bonds completely eclipse, okay? So this front bond is right in front of this rear bond here, okay? So the bonds are completely eclipsed. Now, what are bonds made out of? Electrons, right? Bonds are made out of electrons. They're shared electrons. Electrons are negative. Negative charges repel negative charges. So what we're going to find is that these bonds do not like being eclipsed. They don't like being that close to each other. So what's going to happen is it will rotate, okay, so that these bonds are as far away from each other as they could possibly be. Now, we're not talking about the actual groups or the actual atoms. We're talking about the bonds themselves. So let's talk about conformations of ethane. So so this is one conformation, okay? Well, if I can get it exactly right. I'm trying to get it where it's exactly eclipsed, but my bonds are a little crooked on my modeling set. Okay, there, that's really close. So this would be the eclipsed conformation, where this front bond here is exactly in front of this rear bond here. Okay, so this front bond is exactly in front of this rear bond. So we call this an eclipsed conformation because they're exactly together. And then we have a staggered conformation. We have a couple other conformations that we're talking about. But we cannot isolate these pure conformers because the molecules are constantly in motion, okay? But we can figure out the stability of them. Okay, so here is my ethane molecule, okay? And I have the purple on there because I'm going to show you something in just a minute. But what this picture is saying, and this shows you how to view a Newman projection, okay? So Newman projections are the best way for us to judge the stability of a molecule and to even draw conformers of those molecules. So if we take our eye and look from one side and we look down this central bond, okay, this is the way I've been showing you, okay, then we can come up with our Newman projection where we have our front carbon directly in front of our back carbon. Okay, so our eye is looking straight down this bond here. I hope you can see this. Okay, so this Newman projection that is on the PowerPoint is called a staggered conformation. Okay, and a staggered conformation is where, oh, hold on, it's got this on the top. There we go. Okay, so is where the bonds are as far away from each other as they can possibly be. Okay, so what we're looking at is here, okay, we have 3 hydrogens, 1 going up and 2 going down to the side. And in the back, we have 2 kind of coming up and 1 going down. Okay, so look at this and convince yourself of kind of what's going on in this picture. Reconcile it with the Newman projection. Okay, so you can understand how Newman projections work. Okay, now, ethane conformations, we have what's called torsional energy. Torsional strain or torsional energy is where bonds eclipse each other, okay? And we're not talking about the atoms themselves. We're specifically talking about the bonds and the electrons within those bonds. So we have lots of different conformers, okay? So as we rotate around our bond, okay, so here's an eclipse conformation. I'm going to rotate. Okay, so this is 60 degrees. Our energy goes down. Our potential energy goes down. And remember, in chemistry, low energy means more stable. Okay, so low energy means more stable. Okay, so there is one staggered conformation. So staggered means that the bonds are 60 degrees from each other. We keep turning at 60 degrees and we bump into another eclipsed conformation. Okay, eclipse is high energy, not as stable. And we can do this over and over and over again. Okay, so this is just showing you that staggered conformation where the bond angles between the rear carbon and the back carbon and the substituents that are attached to the rear carbon and the front carbon are 60 degrees apart. Now, let's think about propane. Okay, let me grab another card. Well, yeah, let me grab another card. Break up my cyclohexane that I built. Bear with me. Okay. Not cyclo, just propane. Okay. I said cyclohexane, that got my name. Okay. Blah, 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 blah. Okay, so here we have propane molecule. Okay. When we look down the bond, okay, so one of the bonds for cyclopropane, our Newman projection in the staggered conformation, in the front, we're going to have our 3 hydrogens. Okay. And in the, I can hold this, there we go. In the front, we have our 3 hydrogens. So compare this here to hydrogen, 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 the black hydrogens on the Newman projection. okay? And in the back, we actually have hydrogen, hydrogen, methyl group, okay? So we can draw propane, butane, these kind of things also as Newman projections. We just have to know which bond we're looking down, okay? So this is staggered conformation. The white kind of goes away on the hydrogens, of propane, okay? So just like with ethane, the staggered conformations of propane are always lower in energy than the eclipsed conformations. Now, especially since the methyl group occupies more space than a hydrogen, the potential energy is even higher for propane than for ethane. Now, butane is even more complex, okay? And we're going to talk, so butane actually has two other conformations, or conformations that have two different names. And I'm going to show these to you where you can see. I think I can. Okay. Now with butane, we almost always, so here's butane. 1, 2, 3, 4, okay, and then filled with hydrogens. Go back a little bit. We're going to look down this central bond, okay, so this bond here, right here, is the one that we're going to look down, okay. So remember, these can rotate around this central bond here, okay, and that's exactly what we're looking at, okay. So we can have totally eclipsed, which is where both of our methyl groups are at the top, okay? So our eclipsed bonds, okay, are between our methyl groups. So we're going to look here, okay, and our totally eclipsed. So we're going to look down our central bond. Both of our methyl groups are at the top. And then if we look down here, these are also eclipsed. Our hydrogen bonds, our bonds between our carbons and hydrogens, are also eclipsed, okay? If we turn that 60 degrees, we have what's called a gauche conformation, and it is a staggered conformation. It's kind of hard to hold, okay? It is a staggered conformation in that none of the bonds are directly eclipsed, okay? But this methyl group and this methyl group are uncomfortably close together. They're uncomfortably close together. Now, this is lower in energy than our totally eclipsed butane conformation, okay? But not as good as we can get. Now, if we turn another 60 degrees, we have another eclipsed, but it's not totally eclipsed because we have a bond between a carbon and a hydrogen that is eclipsing this back methyl group. And then we have a carbon and a hydrogen that's eclipsing the front methyl group, okay? So those groups themselves are not forced very close together, but the bonds are still eclipsing, and it doesn't like it. So our most stable conformation of butane, okay, is kind of how we started in the beginning. It's called the anti-conformation. So we have a methyl group at the top in the back and a methyl group at the front in the bottom, okay? And we have no bonds that are eclipsing. Okay, so you need to understand these conformations. So gauche conformation is where it's staggered, but the methyl groups are only 60 degrees apart. Anti is where it's staggered and the methyl groups are 180 degrees apart, and it's much happier there. Totally eclipsed is where the methyl groups are 0 degrees apart. Okay, hope that helps. Here you can see our totally eclipsed is very high in energy. It's not very stable, doesn't like to be there. If we turn it 60 degrees, we can get to our Gauss conformation, okay, which is not our lowest energy possible, but way better energy conformation than our totally eclipsed. Then we can get to our eclipsed where we have our carbon-hydrogen bonds that are eclipsing our carbon-methyl group bonds. But then our lowest energy is going to be our anti-conformation, where we have methyl groups that are 180 degrees from each other. Now let's talk about steric strain, okay? So our totally eclipsed conformation of butane here, it's also shown probably better right here. So far we've only talked about torsional strain. Torsional strain is when bonds eclipse each other, okay? When bonds eclipse each other. Steric strain is when we have two groups or two atoms and their substituents, okay, that are forced too close together, okay? Now remember, our nuclei of our atoms are positively charged, but also the electron clouds of these atoms here are going to end up being very close together, and they do not like being that way, okay? So the totally eclipsed conformation is higher in energy because not only do we have torsional strain from the eclipsing bonds, we also have another kind of interference that's called steric strain. And steric strain is when two groups are forced so close together that their electron clouds repulse each other. Okay, they don't like being that close together. So the kind of interference between two bulky groups is called steric strain. And you can see, especially in the space filling model, how close together these groups are forced to be. So higher alkanes. As we elongate our carbon chains, we find that higher alkanes also resemble butane in their preference for anti-conformation and Gauss conformation about the carbon-carbon bonds. Okay, so it doesn't really matter how long it is. It's going to follow the same pattern as butane as far as conformations go. Okay, now we're going to talk about cycloalkanes now, and I'm going to start rebuilding while I'm talking. I'm going to start rebuilding my cyclohexane molecule that I had built before I took it apart. So these are some examples of different cycloalkanes, and cycloalkanes are just like straight chain alkanes, except that they have less hydrogens because they're connected to each other. Okay, so a three-membered little cyclopropane group has 3 carbons in it, shaped like a triangle. Okay, and these are going to have CnH2n numbers of carbons. Okay, so we're not going to have the +2 because part of the +2 is has been taken away because it has folded in on itself and made a ring. Okay, so you can see we can move and get bigger and bigger rings. We're going to talk about ring strain as well. Okay, almost done. You can fast forward if this takes too long. Let me make sure I have it right. There we go. One more, because this is going to become important. Okay. So cyclo, we use the prefix cyclo to represent anything that has a ring, okay, or it's kind of attached, folded back in on itself. Okay, so physical properties of cycloalkanes. They're nonpolar, just like regular alkanes. They're relatively inert. They're stable. Inert means stable. We can use them for solvents, things like that. It's great if they're a liquid at room temperature. And boiling point and melting point depend upon the molecular weight. So the more molecular weight we have, the higher the boiling point. Okay, so it follows the same general pattern. Okay, so let's talk about how we name these, how we name cycloalkanes. It's very, very similar to naming straight chain alkanes. The cycloalkane is the main chain, and the cycloalkyl groups attached to the cycloalkane will be named as alkyl groups, okay? If only one alkyl group is present, then no number is necessary. So if we only have one there, we're not going to use a number. So for example, this is a methyl cyclopentane. We only have one, so that's definitely going to be carbon number 1, but we don't have to write that. We just say methyl cyclopentane. Here's tertiary butyl cycloheptane. We have a tertiary butyl group shaped like a T, okay, coming off of our cycloheptane. Heptane is 7 members, 1, 2, 3, 4, 5, 6, 7, okay? Now, here we have a complex group. This complex group is a propyl group, 1, 2, 3 carbons long, and we have 2 methyl groups coming off of that propyl group. So this would be 1, 2 dimethyl propyl, in parentheses, cyclohexane. Practice your nomenclature on Nomenclature 101. If there are 2 or more substituents, we number the main chain to give all the substituents the lowest number possible. Okay, so here we would number 1, whether that means going counterclockwise, counterclockwise or clockwise. We don't have a process there except that we want all of our numbers to be the smallest possible. Okay, so 1, 2, 3, 4. So we have substituents at 1 and 2, not 1, 2, 3, 4, because that would give us substituents at 1 and 4. 2 is smaller than 4, so we want to go counterclockwise in this situation. Here we're going to actually number clockwise because that would give us substituents at 1 and 3, whereas if we went counterclockwise, it would give us substituents at 1 and 4. Okay, and 1 and 3 is lower than 1 and 4. Okay, you get the picture. Now, the cycloalkane becomes a substituent. Okay, so when do we know which is the parent chain? Is the parent chain the straight chain alkane that the cyclo is attached to, or is the cyclo always the parent chain? The cycloalkane is not the parent chain if the acyclic portion of the molecule contains more carbons. Okay, so let's look at this. Here we have a 3-membered cyclopropane ring. Okay, but we have this big long 8-carbon chain, 8-carbon alkane chain here. The alkane chain is going to be the parent ring because it has the parent chain because it has 8 carbons, whereas our ring only has 3. So whichever one has the most is going to be the parent chain. Here we have a 4-carbon ring, but we have a 6-carbon chain. The 6-carbon chain will be the parent chain, and the ring will be the substituent. And this one's kind of weird. We have cyclopentyl cyclohexane. Okay, the pentane group is the substituent, and the cyclohexane is the parent chain because it has more carbons than the cyclopentane. Okay, so let's talk about alkenes, okay? And we talked about this in the last chapter. Just real quick, the same way that we said, so we're gonna talk about substituents on rings, okay? When we have a ring, those substituents are locked in place. And we did last chapter talk about cis and trans. And the same process happens when we're talking about cycloalkanes. So here is a cyclohexane. I cannot rotate these guys around this bond. They don't rotate, okay? So when we have a ring, if we have 2 substituents, okay, one on the top face of the ring, so we call this a face of the ring and this a face of the ring. So top face, bottom face, okay? When we have two substituents and one is on the top face and one is attached to the bottom face, we say that they are trans to each other, okay? But if they were both on the same side of the ring, okay, then we would say that they were cis to each other. Okay? Okay. Now, 5 and 6 membered rings are the most common in nature. And the reason is that, well, it's theorized the reason is that 5 and 6 membered rings are the closest stability-wise to that kind of sweet spot of 109.5 degrees between bond angles, okay? When a cycloalkane carbon has an angle other than 109.5, there will not be the optimum overlap of those electrons, and the compound will have what's called angle strain. This is our third and final type of strain that we're going to talk about, okay? So let's review our different types of strain. We have 3 types of strain. We have torsional strain. Torsional strain arises when the bonds are eclipsed with each other, okay? So when one bond overlaps another bond and they're too close, the electrons that hold the bond together are too close to each other. Then we have steric strain. Steric strain is when two bulky groups are too close together and their electron clouds repulse each other. Okay, so torsional strain, we're looking at the bonds. Okay, steric strain, we're looking at the groups or the substituents. And then angle strain arises in cases such as cyclopropane, let me show you, where we have bond angles that are greatly smaller, okay? It's even bending my model set to try to get it into this conformation. So these bond angles here are much, much smaller, okay, than 109.5. Okay, they're 60-degree bond angles instead of 109.5. And because of this, these electrons within these bonds don't overlap very well. Okay, and that causes what we can talk about as being angle strain. Okay, so that's angle strain. Those are our 3 types of strains that we're going to talk about organic chemistry. You need to get them straight in your brain. Okay, so here's an example of angle strain in cyclobutane. Cyclobutane has bond angles of 90 degrees. It's not quite as dramatic as with cyclopropane, okay, but it definitely deviates from the ideal 109.5 bond angle that carbon really likes to be in, okay? So severe angle strain leads to nonlinear overlap of the sp3 orbitals and bent bonds. This is what I was showing you in the cyclopropane that I had put together. What's going on here? Okay, there we go. So those bonds are bent and they don't overlap very well. So they don't like being like that. Okay, let's talk about heats of combustion. Heat of combustion can give us clues about the stability of alkanes, okay? So the heat of combustion is the amount of heat that is released when a compound is burned with an excess of oxygen in a sealed container called a bomb calorimeter. In Gen Chem 1, we do talk about bomb calorimeters and we talk about how we use them. So if the compound has extra energy as a result of ring strain, that extra energy is released in combustion. So we can compare the number of, so we can compare a cycloalkane with that has the same number of carbons as a straight chain alkane, and we can compare to see how much of that energy is due to ring strain. Okay, so torsional strain in cyclopropane. When we have a small 3-carbon ring, okay, we have a lot of torsional strain. I shouldn't have taken apart my cyclopropane. We have a lot of torsional strain because all of the carbon bonds are eclipsed, and so because of that, they're all in one plane, and all of those carbon bonds are eclipsed, and this generates a lot of torsional strain. It contributes to the total ring strain. Okay, now the ring strain of a plane. Okay, so ring strain sounds like a fourth type of strain, but it's not. Okay, ring strain is not a fourth type of strain. Ring strain is if we take our angle strain, okay, which is forcing our bond angles too close together, and our torsional strain from our eclipsing bonds, and we add them together, that gives us our ring strain. Okay, so it's not a fourth type of strain. It's actually our angle strain and our torsional strain added together. Okay, so the ring strain of a planar cyclopropane results from 2 factors. Angle strain from compressing the bond angles to 60 degrees, or with cyclobutane, it was 90 degrees, rather than the sweet 109.5 tetrahedral angle that carbon likes to have. And then also we add in our torsional strain from the eclipsing of the bonds. And both of these 2 factors add together to give us ring strain. Now, cyclic compounds that have 4 or more carbons can adopt a non-planar conformation that helps relieve this ring strain. And the way that it relieves this ring strain is it causes the bonds to not be quite eclipsed, okay? So they're a little bit off. And so cyclobutane adopts a conformation. It's called the envelope conformation, and it's kind of a folded conformation. And that decreases the torsional strain that's caused by eclipsing hydrogens. Now, cyclopentane, okay, is slightly folded. Some books call this a puckered conformation, but it's like the shape of an envelope, okay, but we have one carbon that is bent out of the plane of view. It's like a flap that's folded upward. And again, that causes these side hydrogens. So if we look down this bond angle right here, it causes the side hydrogens to not be eclipsed, which relieves that torsional strain from those eclipsing bonds. Okay, so we're really going to focus in on cyclohexane now and the conformations of cyclohexane. The chair conformation, so I've got my big molecule of cyclohexane here, okay? So a lot of times we draw, of course, when we're drawing on the board, cyclohexane in just a single plane, okay? But what actually happens, because when we have cyclohexane in a straight plane, then all of the carbon-carbon bonds are eclipsed, and all of the substituent bonds are also eclipsed. And this is a very unstable conformation. It doesn't like being this way. It's not happy, okay? So what it does is it will bend one carbon down from the plane of the ring, and then it bends another carbon up from the plane of the ring. And we call this a chair conformation, okay? And mine is probably harder to see than what you have on your screen here. But we basically have 4 carbons that are in the same plane, and then 1 carbon that's kicked up and 1 carbon that kind of droops down here. Maybe that's easier to see if I turn it like that. But you look at this little dude here, okay? It's like a little chair, okay? It's like a chair that you can sit in. Okay? This is the most stable conformation of cyclohexane because the chair ends up having no eclipsing interactions. The bond angles in the chair conformation are 109.5 degrees, and it's the most stable conformational isomer of cyclohexane. We draw it like this, okay, with one carbon up, okay, and you can learn, the more you can practice drawing it this way, okay. And then all of these angles of the hydrogens are important, and we're going to talk about how some of them stick straight up toward the sky and some of them stick out. Okay. Another conformation of cyclohexane is called the boat conformation. Something weird's going on here. It doesn't look like all my bond angles are the same length, but they are. Okay. The boat conformation is where we have 4 carbons kind of all in the same plane, and then we have a carbon that sticks up and a carbon that sticks up on either end. Okay, now these eclipsing bonds, we have eclipsing bonds here, we have eclipsing bonds here, eclipsing bonds here, lots of eclipsing bonds. Not a very stable, the boat conformation is not very stable. Okay, but if it's in this conformation, it can twist and get into what's called the twisted boat conformation, or twist boat, where we have much fewer eclipsing bond interactions and less interference between what are called flagpole hydrogens. And these flagpole hydrogens are this guy and this guy, the ones that stick up are close together on those 2 carbons that stick straight up. Okay. So here are our different conformations of cyclohexane. The chair is the most stable. Here's a chair, most stable. We have what's called a half chair. A half chair is, if you think of like a hospital bed, where your legs are out straight, okay, but your head is kicked up, okay, that would be a half chair. Or a pool lounger, where half of the molecule is planar and then we have one that's kind of kicked up from that. And those are not stable at all. They're the most unstable, okay. And then we have our boat conformation, which is not as unstable as our half chair conformation, but still not nearly as stable as our chair conformation. The boat can relieve a little bit of tension by going into a twist boat conformation, okay, and that's just a little bit more stable. Our chair conformations are the most stable. Remember, lower energy, more stable, higher energy, less stable. So now we need to talk about axial and equatorial hydrogens, okay, or substituents. Okay. Axial bonds are when we're in our chair conformation. I want you to be able to see this really well. When we're in our chair conformation, okay, here we go. In our chair conformation, we have what are called axial hydrogens and equilateral hydrogens. Now, I've already labeled these red and white, okay? Our axial hydrogens, the way that I have this oriented, stick straight up toward the sky and straight down toward the floor. The equatorial hydrogens are around the outside of the molecule, like the equator of the Earth, okay? And the axial hydrogens, we have 3 on the top face and 3 on the bottom face, point up and down like the axis of the Earth. Okay, I know our axis is tilted, but let's pretend it's not. Okay, so when we're in this chair conformation, okay, every carbon has both one axial and one equatorial hydrogen or substituent on it. Okay, and these alternate which are which. So the top face hydrogen is an equatorial but the top face hydrogen on the next adjacent carbon will be axial. Then we go equatorial, then we go axial. So on one face of the ring, as we walk from carbon to carbon, we're going to go axial, equatorial, axial, equatorial on each face of the ring. Now, we can have chair-chair interconversions. Sometimes these are called ring flips, okay? So here, all of my white hydrogens are in the axial position, okay? They're sticking up above and below the ring, and all of my red hydrogens are in the equatorial position. But when I can do what's called a ring flip, in the chair, hold on, it takes me just a little bit. And when I do this, then when I do this ring flip, then my red hydrogens become axial and my white hydrogens are equatorial, sticking out in the plane, in the equator of the ring. Okay, so this is called a ring flip. So remember that the most important result in the chair conversion is that any substituent that is axial in the original conformation becomes equatorial in the new conformation. Okay, so let's look here at this example. This example uses a methyl group here. This methyl group, if we do a ring flip, in this situation, before we do the ring flip, it's in the axial position. But when we do our ring flip, it's in the equatorial position. The equatorial is great for large groups. In fact, it's most stable when large groups are equatorial because they are very far apart from each other, okay? They're very far apart. They have lots of space kind of out here on the side than they do kind of close together in the equatorial positions. So bulky groups prefer to be in the equatorial position, whereas smaller groups are okay being axial. So here's some Newman projections. If we look down the bond, when the methyl group is axial, okay, so he's axial, he's pointing straight up at the sky, that causes a gauche interaction, a 60-degree interaction between a ring carbon and that methyl group. That's not the best place for the methyl group to be, okay? So with an axial methyl group in cyclohexane here, this methyl group, okay, ends up being, if we look here, it's really hard to see on the model because I can't hold it exactly right. But if we look down the bond, it actually causes it to be at a 60 degrees away. Okay, so this methyl group, 60 degrees away from the ring carbon. And because of that, it's not the best place for a bulky group to be. Bulky group prefers to be in an equatorial position. When we have an axial substituent that interferes with axial hydrogens, we call these 1,3 diaxial interactions because they're one carbon apart. Okay, they're one carbon apart. So what that means is when we have these interactions here, okay, so these guys are going to interfere with each other. Okay, they're one carbon apart, so we say 1, 2, 3. So 1 and 3, both axial, diaxial interactions. So it's the interactions between this guy and this guy and this guy and this guy. Okay, so those are diaxial interactions. they can have problems. And we don't see those diaxial interactions when our large groups, we still see them with hydrogens, but with our big bulky groups, it's better for them to be in the equatorial position because we see less 1,3 diaxial interactions. So if you imagine that this is a really giant methyl group, okay, it's going to really interfere with this guy right here. Okay, there's going to be a lot of steric interaction between them. Steric meaning we're forcing those electron clouds too close together. So here are some examples. Here are some examples and the differences between when we have that, whatever it is, okay, in an axial position versus an equatorial position. Okay, so if we have a fluorine, the difference in energy between, so these are just in two different units. These are in kilojoules per mole. These are in kilocalories per mole. When we have the fluorine in an axial position versus an equatorial position, we get 0.8 kilojoules per mole difference in energy. So the axial is going to be 0.8 kilojoules more energy, higher in energy than the equatorial position here. Sorry. Now, this energy difference increases as we get larger, bulkier groups, okay? All the way to this isopropyl group here. This isopropyl group is 8.8 kilojoules per mole difference, whether it's in the axial versus the equatorial position. And here's a tertiary butyl group here, where we have 23 kilojoules per mole energy difference between axial and equatorial. So substituents are less crowded in the equatorial positions. And here you can see, here we have two methyl groups and they're both in the axial position. So these guys are going to be way too close together, okay, way too close together. So they're going to want to both be in the equatorial. I will tell you, okay, what you need to remember is that if we have axial on one carbon, okay, in cis, the next carbon will be equatorial, and then the next carbon will be axial. So as we walk around in the carbons in cis, okay, 1 and 3, so one carbon away will both be axial, okay? So this is something you kind of have to get in your brain, and we can talk more about this in class. So here, these are in cis, so they're both on the same face of the ring, and they're one carbon apart. So they can both be axial or they can both be equatorial. If they're in cis and only one carbon away, one will be axial and one will be equatorial. Here, this is that example. So here, this is this is trans, okay? So trans 1,3-dimethyl cyclohexane. So here we're talking about, oh, they're still at 1 and 3, okay? So we're here, okay, and here. So one is axial and one is equatorial. So both conformations have one axial and one equatorial because it's trans. So it doesn't matter which one is axial and which one is equatorial because they're both methyl groups. And no matter which way we flip our ring, we can't ever get one out of axial and one out of equatorial. Have the same energy. Okay, so let's look at this solved problem. So draw both chair conformations of cis 1,2 dimethyl cyclohexane and determine which conformer is more stable. Repeat for the trans isomer and predict which isomer, either cis or trans, is more stable. Okay, so instead of drawing it, I'm going to use my modeling set. Okay, you can practice drawing these as well. It's hard for me to draw on my trackpad though, something this complicated. Okay, so here is our cheer conformation for cis 1,2 dimethyl cyclohexane. So cis would mean that we're talking about this axial here, methyl, and then if it's cis, okay, on the same face of the ring, the next one is going to be equatorial. Okay, so axial, equatorial on the same face of the ring. Okay, it doesn't matter how we flip it. Okay, the chair conformation is going to be the most stable, and we can't get one out of axial and one out of equatorial. Okay, at position 1 and 2. This one's always going to be axial and this one's always going to be equatorial, no matter how we turn it. Okay, now for the trans isomer, we have on the same face of the ring, okay, let's look at this. At 1 and 2, we have axial and axial on the bottom. Okay, so we have axial on the top here and axial on the bottom. If we flip it, we can get them both into the equatorial positions, and that's going to be the most stable, where both of those methyl groups are equatorial. And that's going to be the most stable. Trans is going to be most stable because we can get both of those groups into the equatorial conformation. So let's look at A. There's 2 possible chair conformations for the cis isomers, and these 2 conformations both interconvert at room temperature. Each of these conformations places one methyl group axial and one equatorial, and it doesn't matter how we flip them, they're going to have the same energy and have the same stability. Now, with trans, we have 2 chair conformations and the trans isomers that interconvert at room temperature. Both methyl groups are axial in one. One is up and one is down, okay? But this is higher in energy. Axial is always higher in energy. But we can do a ring flip where we have a di-equatorial position where they are both in equatorial position. And this is more stable because neither methyl group occupies the more hindered axial position. So if we can get everything in equatorial, that's what the molecule would like. The trans isomer is more stable, especially the most stable di-equatorial conformer or conformation of the trans isomer. Okay, so cis and trans are distinct isomers. They cannot interconvert. Okay, they're 2 different molecules. We have to break bonds to get from cis to trans, whereas conformation-wise, we can do ring flips and move around for axial and equatorial conformations. Draw the most stable conformation of trans 1-ethyl 3-methyl cyclohexane. Okay, so these are at 1 and 3. I'm not going to draw them. Okay, but trans, okay, at 1 and 3. So if we start in axial and we go 1, 2, 3, then whichever is at 1 is going to be axial, and then our 3 is going to be equatorial. Now, as far as most stable conformation, since we have one that's an axial and one that's an equatorial, because we're on the trans, we're going trans, okay? We want our largest, bulkier group to be in the equatorial position, okay? So our most stable conformation is going to be where our methyl group is axial and our methyl group is axial and our ethyl group is equatorial. So we draw the 2 conformations. The ethyl group is bulkier than the methyl group, So the conformation with the ethyl group at equatorial is more stable. So the bigger the group, if you can't put them both equatorial, you always want to put the bigger group equatorial. Okay, so here we have our methyl group axial and our ethyl group equatorial. Okay, so let's talk a little bit. So we're going to completely switch gears and quit talking about conformers of cyclohexane and talk about bicyclic systems. So these are alkanes where we have more than one ring. Okay, and we can have fused rings where these rings share two adjacent carbons in the bond between them. Okay, these are called bridgehead carbons. Okay, when the ring is fused like this. Now, when they're fused, they can be fused in several different ways. Okay, so we can have it fused where the hydrogen, okay, is trans to the other hydrogen, or we can have it fused where the hydrogen is cis to the other hydrogen. This causes it to be bent. Okay. Spirocyclic compounds are rare where the two rings share only one carbon. We have a lot of bridged systems. Now, the nomenclature for these is a little strange, okay? We would write bicyclo, and then in brackets, square brackets, we write 3 different numbers, okay? And I'm going to tell you what these numbers are. And then we would write the name of the alkane. So if our total alkane has 8 carbons, it's going to be an octane. And we say bicyclo. In other words, we got some fusing going on here, okay? So here, this is octane. And what we do is we write the largest number of carbons. So this is a 4-carbon bridge. So this would be 4, 2, 4, 2, and then 0, because these carbons share carbons. There's a 0-carbon bridge here. Okay, and you always write them in decreasing order. So here, this has 2 fused rings, but there's a 1-carbon bridge in between. So we write, hey, I got a 3-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. And this would be a fused ring system. And the name includes all of the carbons in the compound. Okay, so here's Decalan. We looked at Decalan just a second ago. Did I go backwards by accident? No, I didn't. Okay, here's Decalan. Here are our bridgehead carbons. Cis-Decalan has a ring fusion where the ring is attached by 2 cis bonds. In other words, the ring carbons are cis to each other and the hydrogens are cis to each other. Trans-Decalan, we have the 2 hydrogens trans to each other. But trans-Decalan is more stable because that makes the alkyl groups equatorial. Okay, that finishes up chapter 3. So due by Sunday night is chapter 3 homework, and then the alkene and alkyl halide nomenclature dynamic study module. Give me a Canvas inbox if you're struggling with something, and we'll talk more about some of this in class, okay? See you later.